Hi Year 11 and welcome to another science lesson. Today we're going to look at the relationship between kinetic and gravitational potential energy stores. So during the course of last week we looked at several types of energy. We looked at kinetic energy, we looked at elastic potential, and we looked at gravitational potential, and we saw how to calculate each one of those. We also saw how to work out the speed of an object if we knew what its mass and what its kinetic energy was. Today we're going to have a look at how those are all related to each other. But before we move on to that, you need to do your do now. If you haven't done it yet, please pause, go back to the packet and type in your answers. Okay, so hopefully you've had a chance to do that. The first question says, what is the equation for gravitational potential energy? It is potential energy, EP, is mass times gravitational field strength times the change in height. Next, what is gravitational field strength on Earth's surface? So that's the G from our equation, and we need to use 9.8 newtons per kilogram. If we looked at this in key stage 3, then we would have said it was 10 newtons per kilogram. When we go on to A level, it will be 9.81, but for now we'll stick with 9.8. Next, does your gravitational potential store increase or decrease as a person walks down the stairs? So if you're going down the stairs, you are losing potential energy, so your store will decrease. Who would have a greater store of gravitational potential at the same height? Somebody with 60 kilogram mass or 80 kilograms. So if we just look at the equation, if you increase this mass, you increase the energy. So the higher the mass, the more energy you have at the same position. So the 80 kilogram person will have more potential energy. And this should actually read kinetic energy, because that's one of the other ones we're going to use today. I'll change that before I post the packet. So kinetic energy is equal to 0.5 times the mass times speed squared. So we're going to be using these two equations quite a lot today. Both of these we need to recall, so you will not get given this in the exam. You have to remember these. So We'll start off by looking at this chap here. So this guy started at the top of the slope and he's sliding all the way down there, and then we don't really care what happens to him when it gets down the bottom. Let's say he's got a mass of 50 kilograms. At the top he's stationary for the time being, and then as he jumps off the slide, he's going to start to go faster and faster and faster. So his kinetic energy store is going to increase, and the kinetic energy store will be at a maximum when he's at the bottom. So you can't create energy from nowhere, so we have to have been transferring that energy from a different store. When he's at the top, he's 15 meters off the ground, he's going to have quite a lot of energy in his potential energy store. So that's where the energy is coming from. The potential energy will be at the maximum here, and it will be 0 down here. Kinetic energy will be at a minimum here, and it will be a maximum down here. So let's have a look at this with some calculations. We're going to need to use the equation EP equals mass times gravity times the height above the ground. So he's 50 kilograms, and we're on Earth, so we'll assume that gravity is 9.8 newtons per kilogram. Let's note that down over here. This isn't going to change unless we go to a different planet. 9.8 newtons per kilogram, and he's 15 meters off the ground. So 50 times 9.8 times 15 meters, and his potential energy is 7,350, and we're using joules. So his potential energy is 7,350 joules when he's at the top. His kinetic energy when he's at the top is going to be 0 joules. This is because his velocity is 0. He's just stood there, he's not moving, so he's got no kinetic energy. My dog's just come to say hello. Hello, Molly. Where was I? Yeah, so potential energy is at its maximum because he's right at the top. Kinetic energy is 0 because he's not moving. When he starts to slide, this potential energy store starts to empty and this kinetic energy store starts to increase. When he's halfway down, this will be split evenly between the two stores, and when he's all the way down the bottom, when he's here, his potential energy is going to be 0 joules. All of that potential energy has been turned into kinetic energy. So you've emptied this store, you've increased this one. So your kinetic energy, and I don't have to do any more calculations here, all I need to do is copy the number that I had at the top into this one here. So 7350. All my potential energy is converted into kinetic energy. So hopefully that's relatively straightforward. We could even look at halfway. So when he was 7.5 meters, half of this will still be potential, half of it will be kinetic. So half of his potential will have gone, so he'll be left with 3,675 joules of potential, and half of it will be kinetic. So that's 3,675. Now, I'm making a big assumption here. So I'm assuming that there is no air resistance. I'm also assuming there is no friction. If I start to take these two things into account, things get really, really complicated. But we'll keep it simple and we'll just assume that there's no air resistance, no friction. I can also work out something else. If I know something's kinetic energy and I know its mass, I can figure out how fast it's travelling. So if you remember, we had the kinetic energy equation. Kinetic energy is 0.5 times mass times the speed squared. Well, I now know the kinetic energy because it's 7,350. All of the potential that I lost has gone into the kinetic store. So I also know the mass, which is 50 kilograms, so I should be able to work out the speed. I need to do a bit of rearrangement first. So I'll bring both of these down to the bottom on the other side. That will give me kinetic energy over 0.5 times the mass equals v squared. And my problem is I don't want v squared, I actually just want the speed. So I need to square root both sides. And if I square root both sides, that allows me to get rid of this squared. So I can rewrite this as just v. And go back to my pen. So I now have the equation v is equal to the square root of the kinetic energy over 0.5 times the mass. So let's use our numbers from our example over here and see how we get on. So it's going to be the square root of the energy, which was 7,350 joules, divided by 0.5 times 50. We'll pop that into our calculator. And that gives me 17 meters per second. So key points to remember here are that when you're at the top of a hill or when you're on the top of something, you can work out your potential energy by using mass times gravity times the height. If you're stationary at the top of something, your kinetic energy is going to be 0. As you start moving down the slope, your potential energy is converted into kinetic energy. When you finally get down to the bottom, you're going to be left with no potential energy, and it's all going to have been converted into kinetic energy, assuming no air resistance and no friction. So if we had 7,350 potential at the top, we're going to have 7,350 kinetic at the bottom. So we'll have a look at an example of this one. So it's the same idea, but it's slightly more complicated. So I've chosen to do the most complicated example with you, so hopefully the rest will be a little bit easier. So the speed of the rocket just after being launched is 12 meters per second, and the mass of the rocket is 0.05 kilograms. So this is similar, but we're doing the opposite. So rather than starting off with potential and going down, I'm going to start off with kinetic and I'm going to go up. So we've got our rocket at the start here. We're going to work out its kinetic, and its potential is going to be 0. When it reaches the top of wherever it's going, all of the kinetic will have been converted into potential. So its potential energy is going to be 0 joules. Sorry, its potential energy at the bottom is 0 joules, and its kinetic energy at the top will be 0. Let's work out how much kinetic energy it has just as it's launched. So kinetic energy is a half mv squared. 0.5 times, oops, so 0.5 times 0.05, which was our mass from up here. You're going to know it's a mass because it's a kilogram. You're going to know it's a velocity or a speed because it's meters per second. If it's in a different unit, if it's grams or if it's tons, you will need to do a conversion. But this one doesn't ask us to do that. Times 12 squared. And again, never try and do stuff in your head. In a science exam, always use your calculator. 0.5 times 0.05 times 12 squared. Oops. Gives me 3.6 joules. So I can go back to my diagram here and I can show that my kinetic energy initially was 3.6 joules. It seems small, but remember the mass of the rocket is very, very small as well, so that makes sense to me. So 3.6 joules. That means when it gets to the top, assuming no air resistance, then all of my kinetic has been turned into potential. So I don't have to do any more calculations. I just write what I had here up here. So I've now got 3.6 joules of potential energy. So I've done this bit here. I've calculated the kinetic energy of the rocket just after it's been launched. Next, as the rocket moves upwards, it gains gravitational potential energy. State the maximum gravitational potential energy gained by the rocket. So I've done that. That's what I've written here. That's good. Ticking things off as we go. And then I have to calculate the maximum height the rocket will reach, ignoring the effect of air resistance. So I'm done with my kinetic energy equation now. I think I'm going to need to use the other equation, which was my potential energy equation. If we check our DI, our potential energy equation is mass times gravity times height. So mass times gravity times change in height. What I'm interested in is the height. So I'll need to rearrange this to make h the subject. And I'll do that by moving these two underneath. I'll divide everything by mass times gravity. That will give me change in height equals potential energy divided by mass times gravity. We know the mass, it's given to us in the question, it's up here. Gravity, well, we're assuming that we're on Earth, so I'm going to use G is 9.8 newtons per kilogram. It's always good to remember this, but chances are they'll give it to you in the question. So I need to figure out what potential energy was. When it's at its maximum point, when it's at the top, when it's up here, that was 3.6 joules. So that's 3.6 divided by mass, which was 0.05, multiplied by gravity, which was 9.8. So I'm going to pop that into my calculator. And that gives me the answer of 7.34 meters. So I'm just going to round that to 7.3 meters. And you'll notice when I've done my calculation and I've written down my answer, I'll underline what those key things are. So I've got my 7.3 meters. That's answered this last part of the question, and I've answered the first one here with the kinetic energy. Yep, 3.6. That's done. And I've got my potential energy, 3.6 again. Things to watch out for, again, unit conversions, make sure you're doing that. Make sure you're rearranging your equations correctly. So if you struggle, you can use your equation triangles. So your potential energy, mass, gravity, change in height. If we're working change in height, working out change in height, we'll cover this one up. We're left with potential energy divided by mass times gravity, which is exactly what we got earlier. Again, I would recommend watching this direct instruction video twice. Okay, there's quite a lot to get your head around, so watching it at least twice should help with that. So there's a couple questions for you to have a go at that use these ideas. So the first one is, we have a roller coaster, starts at point A, which is 35 meters from the ground. We need to calculate the speed of the roller coaster at point B. So, and you need to follow these steps. This is exactly what we did in the direct instruction, so you need to follow these steps exactly. So work out the potential energy at the top, which will be the same as the kinetic energy at the bottom, and then substitute that into this equation. So you're going to be using this equation. For the last one, or sorry, for the next one, you have a passenger that's lifted up a height of 8 meters. They've got a mass of 60 kilograms. You work out their gravitational potential energy. Unfortunately, as they get to this point, the rope breaks and they start to fall back down. So as they fall, all of the potential energy that you've calculated is going to get converted into kinetic energy, and then you would do V equals square root of kinetic energy over 0.5 times the mass to work out the speed just as they hit the water. And then a similar example, work out how much energy they've lost. This time you need to think about why isn't their speed going to be what we'd expect. So what do they have in this situation where we didn't have in this situation, or this situation, or this situation? So what energy store is present, where is that energy going to go? Thank you very much.